is equal to a times L sub t plus 1 plus b times c sub t plus 1. Any questions about why that's true? Or and now I can solve. I'm trying to get rid of a b sub c plus b times c sub t plus 1. That's one thing about difference equations. They are definitely a written language. They are not a verbal language. I can solve for this. I just need to subtract that off. So that's going to be L sub t plus 2 minus a sub L sub t plus 1. Is that okay? And since I've solved for it, now I can take this right here and substitute it where the b times c sub t plus 1 is in that equation there. And I end up with n L sub t plus 1 minus all of this stuff, L sub t plus 2 minus a L sub t plus 1, and that's equal to na plus nb times L sub t. All right? Clever. Very clever. All right. We can multiply out, combine like terms, do some things like that. So that's minus L sub t plus 2. And then we would have plus n minus a L sub t plus 1 is equal to na plus nb L sub t. So we've accomplished sort of half of what we wanted to do. We've eliminated one of the variables. We've eliminated the c sub t. And we have just one difference equation, and it's just in terms of L.
Should that be n plus a? Distribute the negative.
Yeah, thank you. Once spent half an hour in my introductory PDEs class trying to hunt down a lost negative sign. I'll confess I just wave my hands and say, obviously we lost a negative sign, it's back there somewhere. And we'll move on. But, so, we've got that. We have it down to, we've eliminated the c sub t. We have our system combined down into a single equation that just has the lake trout population in it. So, that's good. What's the bad news?
We have N, A, M, and B.
Well, I mean, those are just numbers out there somewhere. So we could pick numbers and put them in, and I would just have 3 and 5 sitting over here or something like that.
You have 3 different timestamps on your own.
So far in all of the homework that you've done, you've never done more than one time step. And here we're doing how many? 2 time steps. That, by the way, just to give you a little terminology, makes this what we call a second order difference equation. So far you've just been dealing with first order difference equations. Now we have a second order difference equation. Anybody in here had 316? Okay. Then you know there's a very, very tight analogy between this and differential equations. So this is essentially the same as having a second order differential equation versus a first order differential equation. Huge similarities there. If you haven't had 316, just ignore that I said anything. Assume that I'm just a blip in time. We did 2 time steps. We're now down here and we're ready to go. Alright, so the question comes out, well, how do you solve one of those? I know how to solve if I only have 1 time step, but what if you have 2 time steps? How does that work? And so we're going to have to do a little ingenuity. If you have an active mathematical imagination, and this is something to try and cultivate, you would look at that and you would say, if I cross my eyes fuzz my vision, take off my glasses, or put on somebody else's glasses. It looks, in an analogy sort of way, like a
Linear.
what would be linear?
Quadratic.
Looks like a quadratic polynomial. Sure. So if we go back and think about, well, how do we go about solving quadratic polynomials? And you think, well, when I dealt with polynomials, I always got a 0 on one side. So let's come back to this and let's put a 0 on one side. So I'll just move everything over to this side over here. So I would add L sub t plus 2 to both sides. I would subtract the n plus a times L sub t plus 1. This was already on that side, so it's not doing anything. And I would have a 0 on one side. Now, if we had the time, if this were a true discrete dynamical systems class, we would show you that the analogy is almost exact. That you can actually solve this exactly the same way that you solve quadratic polynomial equations. You can even use the quadratic formula.
Whoa.
Yes.
Oh wait.
No way.
Now, we're going to see it in a not quite its full glory. We will get to the quadratic polynomial, but we'll do it in a little messier, hands-on way, rather than seeing it in its full theoretical glory. The way we're going to do it is we're going to stop and think about this for a second. L sub t is a function. So really, this is the same thing in essence as taking a function and evaluating it at t plus 2. This is the same thing as taking that same function and evaluating it at t plus 1. And then this is evaluating it at t. The fact that I have a 0 over here means these are just numbers that I have sitting out in front. So what that means, the fact that I have a 0 over here, is in essence, when I evaluate this function at t plus 2, t plus 1, and t, and get the stuff that comes out of those functions, they must cancel each other out. Well, if they're going to cancel each other out, they're going to have to look the same. So when I plug t plus 2 into this function, I have to end up with essentially the same object coming out that I get when I plug in t plus 1 or t. Now, lest you think that just happens automatically, if you take something as simple as a quadratic polynomial, if I plug in f of x plus 2, what happens?
Squared plus 4x plus 4.
Suddenly I pick up terms that don't look anything like the one I already had. And so there's no way I could expect to combine these two and get everything to cancel out, because up here I just had x squareds, but down here I have x's and constants. So with a lot of functions, if you had a logarithm, for instance, and then you do it at x plus 2, well, there's no way I can combine those two functions. I have no laws of logarithms that deal with addition inside of the logarithm. There's no way to split that up or recombine things or get those to stick together somehow. So for a lot of our functions that we can write down, plugging in an x plus 1 or an x plus 2 really does give us something that's incompatible with the previous function.
So what happened when you did that f of x plus 2? How'd you get x squared?
Oh, this is, so you just plug this into that, so now you have x plus 2 squared.
Oh, I see
And
that.
you multiply it all out and you get that.
Okay.
Alright, so moral of the story is just that it is asking for something fairly significant to say that L sub t plus 2, L sub t plus 1, and L sub t all give you exactly the same kind of function. So now we have to rack our brains and say, have we ever seen a function where that's true. That if you plug in t plus 1 or t plus 2, basically all you get out is a multiple of what you already had. Linear, okay. Now if I have something like x, f of x plus 2, little different. If I have mx, the fact that I get the slope times this thing adding on means I'm not going to get a multiple of the function out. I'm going to get something that actually is more complicated than just a multiple.
I might have missed it, but how do we know that all of those functions look the same?
Because when I get done, they have to be 0. So whatever I got over here has to cancel out the stuff that I got over here and over here. So in order for them to actually be able to cancel out, they have to end up being the same kind of object. The only difference is they might be multiples of each other, because I am multiplying by numbers here, and so, you know, it might be one multiple of it versus another multiple of it. But they've got to be the same kind of object, or else they can't cancel out. Crystal?
Well, could you use maybe like a sine or cosine therapy?
Okay. So, if I have sine of x, and then I look at sine of x plus 1, is there any way to combine those two to get them to cancel each other out? There is if I finely tune the period of the sine function. So that when I add 1, so it has period 1, and then by adding 1 I would have exactly the same sine function coming out. But unfortunately in that case it truly is exactly the same thing. And so then I have to count on these numbers being just right in order for things to cancel out.
Can you do something with some sort of exponential function?
Ah, there we go.
Because then you have like a base and you're just raising it to different powers, so you can combine them.
Because if we look at an exponential function, so suppose you have 2 to the x. If I look at plugging in x plus 1, what I get is that's the same as 2 to the x times 2 to the 1, and that's just 2 times 2 to the x, so it's just a multiple of the function that I started with. And that's what we want to see. I want it to just be a multiple. Whatever we get here, we just want it to be a multiple of what we were getting over here and over here. The other clue that we would be interested in exponential functions is that what have the solutions of all of your first orders look like? Exponential functions. So we say, you know, it worked once, maybe it'll work again. So we will try L sub t being equal to R. No, that's R. What do I use? Beta?
Yeah.
Beta. Beta times R to the t. So it's an exponential function, simple exponential function. I guess we'll go over here. One time when I was teaching differential equations,